In this video, we solve homework problem 13.8.024 from the Larson and Edwards Calculus Early Transcendental Functions 7th edition textbook. This is on the section on optimization. We've got functions of several variables, usually functions of 2 variables in Calculus 3, and we're trying to find relative extrema and saddle points. And we're going to use the second partials test. And I've also added a step about the Hessian Matrix, which is not often mentioned in Calculus 3, but it's important in vector calculus, so I introduce it to my students. So I'm going to show you how to do that here. And if you are a student that's not in my class, you can skip that step, but I'll show you how to use it anyway. I'll show you how to use the Hessian and how it's related to the second partials test. Okay, so this is our function, and we want to find all relative extrema and saddle points of the function. I can see why my student asked about this question, and we've got a lot going on here. So we know to find relative extrema or saddle points, the first thing we need to do is find the critical points of the function. And remember, whenever you're finding critical points, you're finding the points where the gradient vector of that function is the 0 vector. So let me write that down. So we're looking for all x naught, y naught, such that the gradient of the function evaluated at x naught, y naught is the 0 vector. So the slope in the x direction is 0 and the slope in the y direction is 0. So that means you're going to be at a flat spot on the graph. You could be at a hill, you could be at a maximum, a relative maximum or a local maximum, you could be in a valley. That could be a local minimum or a relative minimum, or you could be sort of at a pass where it's the local minimum in one direction and local maximum in the other direction. That would be a saddle point. So we need to find the gradient vector and then set it equal to 0, the 0 vector, in order to find those critical points. So let's look at this guy. In order to find the gradient, we have to find the partial of f or z in this case with respect to x, and the partial of f or z in this case with respect to y. So I'm going to label this f of x, y. Given that label, the gradient is that vector, and we just need to compute a couple of partial derivatives. All right, so this is a function of x and y, and this is a function of x and y. So when I compute the partial of this with respect to x, I'm going to have to use the product rule. So I've got a function of x over here times a function of x over there. Let's do that. If I think of this as my first function, and this is my second function, remember from Calculus 1, we take the derivative of the first, and we multiply it by the second function, undifferentiated. And then we add the derivative of the second function with respect to x, treating y as a constant, times the first, undifferentiated. Okay, so we're here, and now I just need to compute this derivative and this derivative. If you wanted to, you could have computed them in that step. I just like to write this out for students because it really helps you remember what you're supposed to do next. And it also helps you to not get lost as you're doing this. Sometimes I'll see students try to do this all in one step, and they'll forget to multiply by this function at the end or something like that. So we've got derivative of the first times the second plus derivative of the second times the first. The first function, its derivative with respect to x, if we treat y as a constant, is just 0 minus 2x for that piece, and there's no x in that, so it's constant with respect to x, so we get 0. So this guy is the function negative 2x. Now this is e to some power, and that power involves an x, and it's not just x, it's a function of x. So we have to use the chain rule, where this is our inside function. So we've got here the derivative of the outside, according to the chain rule, derivative of the outside evaluated at the inside times the derivative of the inside. The derivative of e to some power is e to that power. And then we're multiplying by the derivative of the inside, oops, that's with respect to x, treating y as a constant, by the chain rule. And don't forget to bring this other guy down. You're not doing anything with it, you're just sort of bringing him down. The derivative of this with respect to x is 0 minus 2x, and there's no x in that, so we get 0. Derivative of that, we're treating it as a constant. Derivative of a constant with respect to x is 0. So we've got this now. Now it looks kind of messy, but it's this quantity, this times this, plus the derivative of this, which is that times that times that. So if I were to write it all in one line, it would look like this. Okay. Now we're going to set this equal to 0, so it's helpful if we can factor it. Now, I know this is not a polynomial, so technically these aren't terms, but I'm thinking of them like terms. They're separated by this minus sign, or I can think of that as a plus, a negative. I'm thinking of this as a single term, and then this is a single term in this quantity. The easiest way to factor this is to factor out the common factors from this term and this term. Well, I can see right away that they both have the exponential in common and they both have the negative 2x in common. So I'm going to take that out, or factor that out if you prefer. And then we're just doing some algebra. So you ask yourself, this times what gives me my first term? And that's just a 1. And then you say to yourself, this times what gives me my second term? We already got rid of the negative. The only thing that's left over here is this piece. So we write that in. And then when you multiply all of these guys together, the 1 plus the 1/2 is 3/2. Okay, so that's our partial with respect to x. Now we're going to do the same thing. We want to compute the partial with respect to y now. Almost the same thing. So again, we're going to have the derivative of the first with respect to y this time, treating x as a constant, times the second, undifferentiated, plus the derivative of the second with respect to y, treating x as a constant, times the first. Okay. That's a constant with respect to y, so we get 0. X squared is constant with respect to y when we take partial derivatives, so we get 0. And the derivative of y squared is 2y. And then I've got e to some function of y, so I have to use the chain rule. This is my inside function. The derivative of e to some power is e to that power, times the derivative of the inside with respect to y. And the derivative of the inside with respect to y is 0 minus 0 plus the derivative of negative y squared, which is negative 2y. So when we multiply all those guys together, we get this, 2y times the exponential. And then I have a negative 2y times that exponential, times the quantity 1/2 minus x squared plus y squared. And then I'm looking at this again as two separate terms. I'm using that term pretty loosely. Just looking at this quantity and this quantity, and I'm saying to myself, well, what do they have in common? Well, they both have the 2y and the exponential. So I will factor that out. And then again, we do the algebra thing. We ask ourselves, this times what gives us this? It's just a 1. and then this times what gives us this. Careful here, that negative was not factored out this time. So you've got a -1 times that quantity, and you want to remember to leave this in parentheses, or you want to remember to distribute that negative. If you leave the parentheses off, your signs are going to be wrong and you're going to get the wrong answer. So let's distribute the negative. We've got 1 minus 1/2 plus x squared minus y squared after distributing the negative. Oops, here we go. And of course, we can simplify that. So that is 2y times e to the negative x squared minus y squared, and the 1 minus 1/2 is of course 1/2. Okay, so those are the components of our gradient vector. And we need the gradient vector to be equal to 0. So I've got the partial of f with respect to x, which is this function, times I hat plus this function times j hat, or this function was the simplified version of it, wasn't it? Now this looks really bad, but it's actually not too bad at all. Once we remember a property from algebra, it's going to be pretty simple. So that's equal to the 0 vector, which is just the vector with components 0 and 0 if we're in 2D. Okay, so this has to be 0 at the same time that this is 0. So setting the gradient equal to 0 is equivalent to saying, I need the partial of f with respect to x to be 0. And I need the partial of f with respect to y to be 0 at the same time. The critical points are the set of all xy pairs where that happens. Okay, so I need the partial of f with respect to x to be 0. Now I like to bring this, or split this up into several cases. This needs to be 0. In order for this to be 0, one of these factors that makes up the partial of f with respect to x has to be 0. So we've got this times that. And the only way that product is 0 is if one of the factors is 0. So either 2x equals 0, or the exponential equals 0, or this guy equals 0. So you basically have 3 cases there. The only way this partial of f with respect to x is 0 is if this is 0, or this is 0. This one's really easy to solve. We divide by -2 and we get x equals 0. Now this one looks difficult, but it's actually not too bad at all if you remember how the exponential function behaves. Remember from pre-calculus that the exponential function looks like this. And remember this 1 minus x squared minus y squared, it means it's a function of 2 variables, but it's really just a number. It's e to some power. From this, I can see that e to some power is always going to give me a positive answer, even if x was, say, -1 million. Let's say it was. Let's make it -1,000 so I don't have to write so many zeros. Remember our exponent properties, that's really 1 over e to the 1,000th. So what that is 1 over a very large number, and 1 over a large number is a very small positive number. So the range of this function is 0 to infinity, not including 0. You're never going to get a 0 out of this. There is no way that y can equal 0. So e to some power is never going to equal 0. So you don't have to worry about that. So that's gone. You're down to 2 cases now. You've got x equals 0 or this guy. You could solve this for x in terms of y, but we won't. I'm going to think of this as case 1 and that as case 2. So in case 1, this is one way that the partial of f with respect to x is 0. We have the partial of f with respect to x is 0 when x equals 0. Now, we need the partial of f with respect to y to be 0 at the same time. So we will have this. That's our partial of f with respect to y. And this is equal to 2y times e to the 1 minus y squared times 1/2 minus y squared when x equals 0. So that x is 0 and that x is 0. So the x's are gone and we're left with this. So okay, you say to yourself, this has to be 0, and it is if x equals 0. And if x equals 0, the partial of f with respect to y is equal to this. So now we set this equal to 0 and find out what y would have to be when x equals 0. And again, we've got a product. This times this is 0. The only way that product is 0 is if one of the factors is 0. So we kind of got a sub case here. If this is case 1, I can think of this as case 1a. X is 0 and 2y equals 0, which of course means that y equals 0, which implies that xy equals 0, 0 is one of our critical points. Okay, so notice what I did. I figured out one case or one way that we can make this partial of f with respect to x equals 0. And then I said, if that's true, what happens to the partial of f with respect to y? In that case, partial of f with respect to y looks like this. And this is 0 if this is 0. That's one possibility. Another way that this would be 0 is if this factor is 0, but exponentials are never 0. So that's not a case. We won't worry about it. It's the same argument, or we could use the same argument here that we used here. E to some power is never 0. The second case, oops, it's actually case 1b, is if the partial of f with respect to x is 0 because x equals 0, and this guy is 0, then the partial of f with respect to y would be 0, and we'd be at a critical point. So we'll have this guy equals 0. So you want to solve that for y. Take the square root of both sides and rationalize that denominator. Okay. That step's not necessary unless you're a math teacher and you really like rationalizing things. I believe WebAssign would accept the answers either way, but that's the y value. Now remember our assumption, x was 0 in this case. So we've actually got 2 critical points from case 1b. We can have x equal to 0 and y equals positive square root of 2 over 2. Or x equals 0 and y equals negative square root of 2 over 2. That's the other possible critical point. Okay. Now that's all associated with case 1. So we actually got 3 critical points from that. Now case 2 occurs when this is equal to 0. This one is a little bit harder, but with algebra, we can still substitute and we'll still be able to solve this. Oh, I wrote this partial of f with respect to x, not y, sorry. So in this case, our partial of f with respect to x is 0 when this is 0, and we still have the partial of f with respect to y is equal to this. Now this seems pretty difficult, but it's actually not too bad. You might say, I can't just substitute that in here somehow, can I? Actually, you can. And the reason why you can is because this equation involves a negative x squared plus y squared, and this equation involves an x squared minus y squared. Do you see the relationship between that and that? If I take this and I multiply it by -1, I get that. Or alternatively, you can think of it this way. You can take this equation and solve for x squared plus, or x squared minus y squared. If we add x squared to both sides and subtract y squared from both sides, we get that. Adding x squared over there and subtracting y squared over there. So x squared minus y squared must be 3/2. So that's actually 3/2 when this is satisfied. So the partial of f with respect to y is 2y times the exponential times 1/2 plus 3/2, which is 4/2, which is 2. And we need that to be equal to 0 at the same time that this is 0. Well, we already know the exponential can never be 0. So I've got 2y times the exponential times 2 is equal to 0. The only way that happens is if 2y equals 0. And we know that happens when y equals 0. Now, I don't know what x is yet, but I know that y equals 0, and I know that 3/2 minus x squared plus y squared has to be 0. So we can take this y equals 0 and substitute it in up here, and we can solve for x. So we've got 3/2 minus x squared plus y squared, which is 0, equals 0. So 3/2 equals x squared. So x equals plus or minus the square root of 3/2. Or if you prefer to rationalize, you can multiply by √2 over √2, and you get square root of 6/2. Okay, in this case, we have 2 more critical points. X is equal to positive square root of 6/2 when y equals 0. And x is equal to negative square root of 6/2 and y equals 0. Okay, so we actually have a lot of critical points to test. This doesn't often happen, but it does happen with these polynomials times exponential functions, as you can see. And our list of critical points was 0, 0, 0, and square root of 2/2, and 0, and negative square root of 2/2. And then we had these guys that we just found. Okay, this is a long video. Hang in there. We're almost there. Now we have to classify each of those critical points as corresponding to relative minimums or relative maxima, relative minima, that's proper English, or saddle points. One way that we can do that is by calculating the Hessian and then finding its determinant at each of those points. Now remember, the Hessian matrix is the matrix of second partials. And I think that's probably why my student asked about this. There's just a lot of derivatives to take here. So remember, our partial of f with respect to x was this. And the partial of f with respect to y was given by this. Now, we could just start differentiating, but I wouldn't recommend that, because notice what you have here. You've got one factor times another factor times a third factor. That is a great way to write it if you're trying to find critical points. But if you're trying to take a derivative, I don't want to have to use a three-factor product rule, which we could easily derive if we wanted to. It would be easier if this was just a product of two things, derivative, and then we could use the product rule, derivative of the first times the second plus derivative of the second times the first. So what I would recommend you do, just to make your calculations easier, is take out the exponential and distribute this polynomial negative 2x into this. And similarly over here, you want to distribute that 2y into that. So we've got our exponential, let's take that out. And then we'll take negative 2x and multiply it by this guy. Negative 2x times this is going to give me a negative 3x. Negative 2x times negative x squared is positive 2x cubed. And then negative 2x times y squared is negative 2xy squared. I am not taking partial derivatives or second partial derivatives yet. I'm just doing algebra. Now I've got 2y times this guy. 2y times 1/2 is just a y. And then I'll have 2 times x squared times y. And 2y times negative y squared is negative 2y cubed. Okay. So now we want to take some second partials. It's very involved, and I'm sorry. Okay. So this is my partial of f with respect to x, and the second partial of f with respect to x means we take this and we take its derivative with respect to x. So we'll have the derivative of the first with respect to x. This time I'm not going to show that product rule step, I'm just going to evaluate it. If this is my first function, this is my second, derivative of the first is the derivative of this function using the chain rule. Derivative of e to some power is e to that power. And then we multiply by the derivative of the inside with respect to x, treating y as a constant. That's derivative of the first. And then we multiply by the second. And then we add derivative of the second times the first. Derivative of the second with respect to x, treating y as a constant, is negative 3 plus 2 times 3 is 6 times x to the 1 less power, that's x squared. And this is a constant times x as far as we're concerned. The derivative of a constant times x with respect to x is just the constant. In this case, the constant is a negative 2 times a y squared. Derivative of the second, and we're multiplying by the first. Okay, factor out that exponential. And distribute the negative 2x here of 6x squared and negative 4 x to the 4th. Negative 2x times this is going to be positive 4x squared y squared. And then I'm adding, well, you're saying to yourself, let's see, let's look at all of this. I have this is one term and this is another term. Again, using the term loosely, they have the exponential in common. I took it out. So this times all of this gives me the first term, and this times this expression in red gives me the second term. And you can simplify if you like. Got a 6x squared and a 6x squared. So it's 12x squared. All right, so we're there. And now we want to compute the second partial of f, or actually a mixed partial of f with respect to x and then y, or y and then x. Either one is fine. So I think I'll take the partial with respect to x, and then differentiate it with respect to y. So I want this. Remember, that notation is the same as that notation. I know it looks like I'm writing them in the reverse order, but that's not how we think about it. We take this derivative first, and then this derivative. And this is read the opposite way. You take this derivative first, and then you take the derivative of that with respect to y. Okay, so we've got the partial with respect to y of all of this. Partial of f with respect to x. Minus, excuse me. And here's hoping we don't make any algebra errors, right? Or even transcription errors, because then we're going to be in trouble and we're going to get the wrong answer. Hopefully that doesn't happen. But I've got a function of y here, and this is a function involving y, so I'm going to have to use the product rule again. That's my first function, and that's my second function. Derivative of the first with respect to y is e to that power times the derivative of the inside with respect to y, which we know by now is negative 2y. Derivative of the first times the second. Plus the derivative of the second with respect to y. There are no y's in that, so that's 0. There are no y's in that, so that's 0. Derivative of this piece with respect to y. Well, negative 2x is just a constant, so I've got a constant times y squared. So I have my constant times 2y. 2y times negative 2x is negative 4x. So I'm bringing that power down and multiplying by y to the 1 less power. That's where that y comes from. That's derivative of the second. And we want to multiply that by the first. Okay, you want to factor this if you can. Yes, we could take out a negative 2y here and here. And we can also take out the exponential. Remember how this works. Think of this as a term and this as a term. Ask yourself, this times what gives me the first term? Well, I took that out and that out. So what's left over is all of that. And over here, I took that out and I took out a 2y, so I'm left with a negative 2x. Oh wait, I took the negative out as well, so I'm actually left with a positive 2x. 2x times the negative 2y would give me the negative 4xy. Okay, and I've got a negative 3x here and a 2x, so I can combine those. It's going to give me a negative x plus 2x cubed minus 2xy squared. And mixed partials happen to be equal. Those guys are the same, so don't worry about doing this guy. It saves us a little bit of differentiation. Okay, last part, second partial for the Hessian matrix. So we're taking the partial with respect to y of the partial of f with respect to y, which was this. Okay. I keep these notes nearby because we're going to substitute those critical points into the Hessian in just a moment. All right, I've got a function of y times a function of y. So I use the product rule again. This is good practice, guys. I know it seems tedious, but it's very good practice. Okay, so we're taking derivative of a product. So we have the derivative of the first times the second with respect to y. Derivative of an exponential is the exponential times the derivative of the inside with respect to y. Done that before, so I'm not talking through that chain rule nearly as much anymore. That's derivative of the first times the second, plus derivative of the second, so I'm going to use black for the plus sign, derivative of the second with respect to y, treating x as a constant. It's the derivative of y with respect to y, which is 1. And this is a constant times y. The derivative of a constant times y is just the constant. And the derivative of negative 2y cubed is negative 6y squared. That's derivative of the second, and we're multiplying it by the first. Okay? Again, we want to think of this is a term and this is a term. Say, what do they have in common? They have the exponential in common. And then ask yourself what's left over. This times what will give me this? I took this out, so I'm left with this times this. I'll distribute the negative 2y. So I get negative 2y squared minus 4x squared y squared. Negative times the negative, it's going to give me a positive 4y to the fourth. And then I say to myself, this times what gives me this? And it's just this. All right, and let's see if we have any like terms. I've got a negative 6y squared and a negative 2y squared. And I think those are the only like terms. So it's going to be negative 8y squared times all of this. Okay, so we just computed 3-second partial derivatives, and then we used a fact to state that this other one was equal to this one. So we've got this guy, and this guy that all need to be evaluated at those 5 critical points. Now that looks tedious, so I'm going to save a lot of the arithmetic and I'm going to do it in my head, but it's actually not too bad because these x's are all 0 here and these y's are 0 here. So it's going to make our calculations pretty easy. So let's do this. I want the Hessian at 0, 0. That means I want these 4 partials, 4 second partial derivatives, evaluated at the point 0, 0. And 0 is really easy to plug in. So I'm just going to look at the function and talk through it with you. If x and y are both 0, I get e to the first. And then this is 0, that's 0, that's 0, and that's 0. And I'm multiplying by negative 3. So I just have a negative 3 times e. At 0, x equals 0, y equals 0. Well, this is 0 because we've got a factor of y here. So the partial f with respect to x and then y is 0, and the same is true for the other mixed partial. And then we want to evaluate this at 0, 0. And at 0, 0, we get e to the first. That's 0, that's 0, that's 0, that's a 1, and that's a 0. So we just get e to the first times 1, which is just an e. Okay. Now, if you want to determine whether 0, 0 corresponds to a minimum or a maximum, you have to take the determinant of this matrix. So the determinant of the Hessian, oops, that should be del squared f, sorry about that. At 0, 0 is typically denoted d. It's denoted d in our textbook. It's just this expression. So that times that minus that times that. And since those are equal, sometimes it's written this way. But we're evaluating all of this at 0, 0. So if your teacher hasn't introduced you to this matrix, you can just find those 4 or those 3 partial derivatives and plug in 0, 0, and you're going to get the same thing as if you were to take the determinant of this matrix. So multiply across this diagonal, we get -3. E times e is e squared minus 0, which is of course -3e squared, and that's negative. Whenever that determinant is negative, or whenever this expression is negative, and that means that that point corresponds to a saddle point. I'm going to say the function has a saddle point at 0, 0. Now the way WebAssign prefers your answer, they're looking for an ordered triple. So they want x, y, z, or x, y, and f of x, y right here. And they are calling that a saddle point. So let's go back to the original function. I know it's been a while since we looked at it. There's our function. At 0, 0, we get a 1/2, and then that's 0 and that's 0. So 1/2 times e. So x is 0, y is 0, and z is 1/2 times e. And if you're wondering sort of what that looks like, remember these two partial derivatives. Remember what they mean. This is the second partial of f with respect to x, and it's a negative number. So that means the graph is concave down in the x direction. And this is the second partial of f with respect to y. That indicates concavity in the y direction. Since that's positive, it's concave up in the y direction. So it's concave down in one direction and concave up in a different direction. And when you put those two pieces together, that corresponds to a saddle. Does that make sense? It's just going to look like that. Okay. So we computed the Hessian, we evaluated at 0, 0. That's the easiest one. We've got 4 more critical points to do, but we can handle it. Okay, so the next set of critical points, we've got x equals 0 and y equals plus or minus square root of 2 over 2. Now normally I would have to treat these separately, but our second partials involve a lot of x squareds and y squareds. So I'm going to take advantage of the fact that this is plus or minus the same number every time I see a y squared. Okay, so let's see what we get at the critical point 0 and square root of 2 over 2. So I want those 4 second partial derivatives evaluated at x equals 0, y equals this. So here's our second partial with respect to x. 0 squared is 0. Square root of 2 over 2 squared, think about that. You're going to get 2 over 4, so that's going to be 1/2. So this is, oh, here we are, this is e to the 1 minus 0 minus 1/2. So that's e to the 1/2 power. Times all of this. Now x is 0. So that guy's gone, that guy's gone, that guy's gone. And we just have a -3 minus 2 times 1/2. 1/2 times the 2 is going to be a -1. A -1 plus -3 is -4. So we have -4 times e to the 1/2. And normally I'd write the -4 out front, but we were just evaluating it from left to right. So that's what we've got. Multiplication is commutative, and we know it's the same thing. Okay. So now we want the partial of f with respect to x and then y evaluated at 0 and square root of 2 over 2. If x equals 0, this is 0, this is 0, this is 0, and this is 0. Since x is 0, all of these guys are gone. So we're just going to get 0 there. And the other mixed partial is also 0. Now we just need the second partial of f with respect to y at 0, 0. And the second, or at 0 and square root of 2 over 2. At square root of 2 over 2, this is 1/2. So we have 1 minus 0 minus 1/2. So that's e to the 1/2. And x is 0. but y is square root of 2 over 2. So this guy is gone, this guy is gone, and we want to evaluate everything else at square root of 2 over 2. And this one, I think I'll write out the arithmetic. I've got negative 8 times y squared, which is 1/2. And then x is 0, so that's gone. And then I've got 4 there, and y to the 4th is the same as y squared squared, so it's actually going to be 1/2 squared, or 1/4. Plus 1, and x is 0. So I end up with negative 4 plus 1 plus 1, that's negative 2, times that e to the 1/2. It's the Hessian matrix. It's our analog of the second derivative for a function of 2 variables. If I want to determine whether this point corresponds to a min or a max, I need to take the determinant of this. And we call that d. Or sometimes people will write it this way. Some students really don't like our using absolute values in this way, but it's totally legal. And you should get comfortable with it because you're going to see it again in other classes. So I want the determinant of this, so I just multiply this times this. Negative 2 times negative 4 is going to give me an 8. E to the 1/2 times e to the 1/2, add the exponents. E to the 1st, that's greater than 0. Remember, whenever d is greater than 0, that means these guys have the same sign. And you can see that they're both negative. That means that, or that second partial with respect to x being a negative number. That means that the graph is concave down in the x direction. And it's also concave down in the y direction because d is positive. Whenever d is positive, these guys have the same sign. You can also look at these two numbers and see that they have the same sign. So it's concave down in the x direction. It's also concave down in the y direction. And so what you get is something that looks like an elliptic paraboloid facing down at that point. Locally, it has this behavior, and that means we have a relative maximum at this point. Now, technically, the relative maximum is just the function value at this point, but that's not what WebAssign wants. WebAssign wants an ordered triple, which bothers me a little bit, but we're going to give WebAssign what it wants, right? So let's say the relative maximum is f of 0 and square root of 2 over 2, which is equal to this. We have a relative maximum at that location, and it's equal to this. If x is 0 and y is square root of 2 over 2, we get, that's going to be a 1/2. 1/2 plus 1/2 is 1. And this will be e to the 1/2, or 1 minus 1/2. So 1 minus 1/2 is 1/2. So we'll have 1 times e to the 1/2. Now that's what I would want on the test. The relative maximum is this, and it occurs at this location. But WebAssign wants the ordered triple. So when you enter your answer there, you want to enter this answer. X is 0, y is square root of 2 over 2, and the relative maximum is e to the 1/2. Okay. Now let's do the same thing at y equals, or x equals 0, y equals negative square root of 2 over 2. You might think, oh my goodness, this is so tedious, but actually we're gonna have a shortcut. Notice that this has a y squared and a y squared in it. There are no y's by themselves. Since there's not a y by itself here, we're gonna get exactly the same answer. Oops, that's the partial of f with respect to x, sorry. Here's the second partial of f with respect to x. I'm gonna put a box around it to make it a little easier to find. Notice that all the y's are squared here. So whatever we got at positive square root of 2 over 2, we're going to get at negative square root of 2 over 2. So that's going to be the same. At x equals 0, y equals square root of 2 over 2. Since x is 0, we still get 0 here, so that's the same. And of course, the other mixed partial is the same. And the same thing happens here. So this actually works when y equals plus or minus square root of 2 over 2. So we have a relative max at this location. And we also have a relative max at x equals 0, y equals negative square root of 2 over 2. And let's look at the original function. Notice the original function has a y squared in it and a y squared in it as well. There are no y's by itself. So everything is going to be exactly the same as negative square root of 2 over 2, even the z value. So we have two relative maxima, one at 0 and square root of 2 over 2, corresponding to a z value of e to the 1/2, and one where the y is negative. Okay, so keep that in mind. You've got two relative maxima, and they're right there. We had a saddle point at 0, 0, but WebAssign wants it this way, 0, 0, and the corresponding z value. Now let's look at the last guy, last two guys. We're going to be able to handle those in pretty much the same way that we handled these two. We've got zeros for the y's this time, and we've got x's that come in pairs like this. X equals plus or minus square root of 6 over 2. All right, so let's look at those second partials. And I think we're going to have the same thing that happened last time, so I'm just going to get ready for that. I want those second partials at that location. X equals this, y equals this. Okay. When y is 0, this guy is gone, this guy is gone. And then we've got some x terms here. So let's figure out what x squared is. When x equals plus or minus square root of 6 over 2, when we square both sides, oops, it's equals, square the numerator, square the denominator, that reduces to 3 over 2. So keep that in mind. X squared is 3 over 2. All right, so here I've got e to the 1 minus 3/2, and you know that that's 1 1/2, right? Y is 0. 1 minus 1 1/2 is negative 1/2, so this is e to the negative 1/2. Over here, I've got 12 times x squared, and x squared is 3 over 2, minus 4 times x to the 4th. And x to the 4th is x squared squared, so we have 3 over 2 squared there. Y is 0, so that guy's gone. We still have a negative 3. Y is 0, so that guy's gone. So this can reduce. We get 18 here. If you square that fraction, we've got that. The 4's reduce. And so I have 18 minus 12, which is 6. So this is 6, and this is e to the 1 minus 3/2, or e to the negative 1/2. So I have 6 times e to the negative 1/2 here. And remember, that's the same as 6 over e to the 1/2. So it's not a negative number, that's just a negative exponent, which just puts that in the denominator. When y is 0, let's go to our mixed partial. Hey, it's going to be 0. Nice and easy. Both mixed partials are 0. And then when x is this number and y is 0, here's our second partial of f with respect to x. Y is 0, so that guy's gone, that guy's gone, that guy's gone. That guy is gone. and I have an e to the 1 minus 3/2 again. So that's e to the negative 1/2. And I get a bunch of zeros, plus 1, plus 2 times x squared, which is 3/2. So you've got e to the negative 1/2 times 1 plus 2 times 3/2. Of course, those reduce and you just get a 4. Oops, times an e to the negative 1/2. And there were x squareds everywhere. There were no x's by themselves. So this works for both plus and minus square root of 6/2. Second partials test involves taking the determinant of this Hessian. Multiply. So you multiply the coefficients, add the exponents there. Don't be, and then you subtract these two guys and multiply. Do this times this, minus this times this. Just get this. Don't be distracted by the negative exponent. It just puts that e in the denominator. It's a positive number. If d is positive, that means you either get a relative max or a relative min. And you can determine whether it's a relative max or min by looking at the signs of these second partials on the diagonal. Now remember, this is the second partial with respect to x, so it gives you concavity in the x direction. And this is the second partial with respect to y, giving you concavity in the y direction. So the second partial with respect to x at that location is positive. So that means it's concave up in the x direction. Whenever d is positive and this is positive, well, whenever d is positive, that means these two guys have the same sign. And we can see it, they do, they're both positive. So it's concave up in the x direction and concave up in the y direction. I'm just gonna put little hash marks. Is that what they're called there? I don't remember, actually. Whatever those little guys are called. It's like just that again. Also positive, so it's concave up in the x direction, concave up in the y direction. And so we have as a relative minimum at this location. So f of these xy pairs is a relative minimum. And if I want to find the corresponding z value, I go back to my original function and I substitute in y equals 0, x equals plus or minus square root of 6/2. Remember, x squared was 3/2. So 1/2 minus 3/2 is -2/2. -2/2 is just a -1. So we've got a -1 and times e to the -1/2 power. Now WebAssign's not going to like that. So we're going to use the ordered triples here. They want xy and f of xy. Oops. Even though that's technically not the minimum. Now if you're saying to yourself, Miss Townsend, why is that not the minimum? Let me ask you, if I asked you for the maximum height of something, would you give me the time and the height, or would you just give me the height? That's kind of what we're talking about here. The minimum value of the function is actually just that number, but WebAssign likes the ordered triples, so we'll give them what they want. When x equals this and y equals this, the z value is this. And when x equals this and y equals this, the z value is the same. Now, as you're doing your homework in WebAssign, make sure you put them in the right order. There's some fine print there telling you that they want the smaller x value first, and the smaller y value, and so on. Make sure you follow those directions if you want to get full credit. I hope that helped.